Dear learners, Assalamu alaikum. Welcome to the channel MAK the Virtual Instructor. So as you know, this channel arises in YouTube to upload videos on different topics on engineering mathematics. As the continuity, we are going to discuss today a new topic, coordinate geometry. We are going to discuss two types of geometry today, two-dimensional and three-dimensional. And we say two-dimensional geometry as the plane geometry, and three-dimensional geometry as the solid geometry. Okay, solid geometry. First, we are going to discuss the types of coordinate systems, and we have two types of coordinate systems. One is Cartesian and another is polar. Okay. Cartesian and polar. Cartesian geometry and the polar geometry. Okay, so for Cartesian geometry, we have one-dimensional case, two-dimensional, three-dimensional, even the four-dimensional. Even we can generalize our concepts of Cartesian geometry up to the n dimensions. And as well, we have the polar coordinates of two-dimensional, three-dimensional, even up to the n dimensions. Okay, now let's discuss first-dimensional Cartesian coordinates, one-dimensional. So in this system, we have just a single axis, single dimension. That's the x-axis, you can see. And that's the positive direction of x-axis. You can say x plus, and that's the negative direction of x-axis. You can say x minus. And the point here, we mentioned 0. You can we refer this point to as the origin. Okay? So in every coordinate system, we have some origins. And in this case, we of one dimension, we are going to mention just a single number as the coordinates, which is 0. We say the origin. So every real number, whatever the number is, either positive or negative, either irrational or irrational, either it's fraction, it can be decimal, it can be fraction or integers. Whatever the numbers are, those all exist in this line, and we call the line is real line. Okay, so for the sake of all the real numbers are exist here on the real line. Okay, let's talk about two-dimensional Cartesian coordinates. And as usual, we have two dimensions, two axes, x and y axis. This is the positive direction of x-axis. This is the negative direction. The upward direction is the positive direction of y-axis, and the downward is the negative of y. Okay, and that's very important to mention here that the origin here is 0, 0. Okay, so we have to mention two numbers, say for example a and b, to refer any points on these coordinates. Okay, and we call these numbers, first number as the abscissa and the second one as the ordinates. Okay, so say for example, if we refer the point 2 and -3, then let's look at the point on the graph. 2 is the positive, in the positive direction of x-axis. That's that we are going to here. And -3 is the negative direction of y-axis. That's downward, right? 1, 2, 3. -3 is here. So 2, -3 is this point. Okay, this point is 2, -3. Okay, I specified here a number of coordinates for your convenience. The point here I referred is 2, 3. I referred a point in the second coordinate, second quadrants, -3, 1, and so on. Okay. Let's talk about now about the three-dimensional Cartesian coordinate system. And as the name says, we have 3 dimensions, 3 axes in this system, and that's the positive direction of y-axis, and it's the negative direction here is the negative direction of y-axis, and that's the positive direction of x-axis, that is the negative direction, right? ADK, negative direction of x-axis. Okay, that's the positive direction. And if I say the upward direction is the positive direction of z-axis, and the downward here in this direction is the negative direction of z-axis. So it's clear that we have to mention 3 numbers. Let's say, for example, A, B, and C. If we refer some coordinates on the 3-dimensional coordinate system, okay? And we are going to say the first number is the abscissa as before, and the B, the ordinates as before, and C, the extra number here is the height, okay? So anything which has 3 dimensions, any object which has 3 dimensions, like length, breadth, and height, is really a solid object, right? So in the 3-dimensional coordinate system, we have every point as the coordinates A, B, C, abscissa, ordinate, and the height. And it's urgent to mention here that the coordinates of the origin here, if we say O, is 0, 0, and 0. Okay, that's the origin. Okay, so it's clear for every point we have to mention 3 numbers, 3 lengths, or 3 figures. Okay, one for the length in x direction, another for y direction, and another for z direction. And everything, every axis is inclined vertically, mutually. Okay, they are mutually vertical to each other. So x-axis is in the right angle with the y-axis. Y-axis is vertical to the z-axis, and so on. Z-axis is the vertical to x-axis. Okay. Let's talk about now the 2-dimensional polar coordinates. Okay, as you know, that we have 2-dimensional, 3-dimensional, even n dimension up to the n dimensional polar coordinates. So this is the 2-dimensional case. Okay, so in 2-dimensional case, we have to refer 2 things, r and theta. Okay, so the first number we are mentioning here is called the modulus, and second one is called the argument. So r is modulus, theta is argument here. Okay, so let's say, for example, 4, 210 degree. So r, the modulus, is 4 in this case, and theta, the argument, is 210 degree here. Okay, so let's know what is r, what is theta. Okay, what are argument and modulus. So first, modulus. What's modulus? Modulus is just the length of the referring point, just the distance from the origin. Okay, so this distance of the referred point from the origin is the r. Okay, the modulus. And what's argument here? Let's say pi or theta, whatever. It's the angle created by the line joining the origin to the point along the positive direction of the x-axis. Okay, so if you say this is the x-axis and this is the positive direction of x-axis, for your kind of information, that we take always the counterclockwise direction is the positive direction, and the clockwise direction we call the negative direction. Okay, counterclockwise direction or anti-clockwise direction is always the positive direction. Okay, so if we refer this point, so 3 is the modulus, 60 degree, or you can say pi by 3 is the argument. Okay, if I refer this point, then this length r, which is 4, is the modulus, and 210 degree, this angle, this whole angle, is the modulus here. Okay, so for any point P, we are going to mention 2 things: a pure number, which is called the modulus, and an angle created by the line of the joining of the point along the x-axis, positive direction of x-axis, is the theta, which we call the argument. Okay. Now it's urgent to show some relations between Cartesian coordinates and the polar coordinates. Okay, and we have the relations x equal to, that's x abscissa is equal to r cos theta, and y, the ordinate, is equal to r sin theta, That's the relation between the Cartesian coordinates and the polar one. Clearly, you can convert any Cartesian coordinates to the polar coordinates, and the reverse thing, you can convert any polar coordinates to the Cartesian one. Okay, using these relations. If I mention some other relations, you can express the modulus in terms of the rectangular coordinates like x square, square root of x square plus y square. Okay, and the theta, the argument, is the tan inverse ordinate by abscissa. Okay, tan inverse y by x. So you can use these two relations to convert any Cartesian coordinates to the polar very easily. Okay, so not only that, you can compare the two-dimensional polar coordinates with your complex field concepts. Okay, so for example, we have a complex number 4 plus 4i. That means 4 is the real part here, and this 4 is the imaginary part here. So as you know, this is the real axis and this is the imaginary axis. So this length is 4 and this length is 4. So, okay, so clearly, this is 4 and this is 4. Okay, so clearly this distance is going to be square root of 4 square plus 4 square. That means square root of 32. Okay, and that's the modulus of the point. Okay, and what's the argument here? So if you find the angle, this angle, that would be the argument. Okay, argument. And I adjust here figure that these angles from 0 degree, 30, 60, 90 up to the 330. These are some standard figures of angles, so that you can mention easily the arguments of the polar coordinates. Okay, so here we have a complete circular angle 360 degree, and I have divided into 12 segments. Okay, so each of 30 degree, or pi by 6. Okay, let's talk about now the three-dimensional polar coordinates, and we have a number of three-dimensional polar coordinate system. Very importantly, this is the cylindrical coordinate system and this is the spherical coordinate system. Okay, in cylindrical coordinate system, we have to mention three things: pi, pi, theta, and z. That means two angles and a height to the center of the cylinder. Okay, and that's the spherical coordinate system, spherical polar coordinate system, in which we also mention three things: r, theta, and z. Okay, r is the radius of the sphere, radius, that means the distance of that point from the origin. Theta is the argument as before, and pi is the new angle here, one extra angle. Okay, that's all about polar coordinates. Not only that, we have a number of more coordinate systems, a lot of more coordinate systems like curvilinear coordinate system, then generalized coordinates for Lagrangian mechanics. Lagrangian mechanics. And we have generalized coordinates for Hamiltonian mechanics. So you have curvilinear coordinate systems, generalized coordinate systems for Lagrangian mechanics. We have generalized coordinate systems for Hamiltonian mechanics, and so on. Okay. So today we discussed coordinate systems, which is very, very important for engineering students. Okay, that's all for today, and thank you very much for being with us. Assalamu alaikum.